equipotential surface, or in short these are called EPS. Okay, so how we can define equipotential surface? So first point, see, first point is that the locus of the points which are at same potential are known as equipotential surface. The locus of all points which are at same potential are known as equipotential surfaces. Now second point, the shape of equipotential surfaces depends on the charge body which is producing electric field. See, the shape of equipotential surfaces depends on source of electric field, depends on source of electric field. So for example, point charge or spherical charge body Okay, if we are discussing about point charge, spherical charge body, so that produces spherical equipotential surface. Spherical equipotential surface. Likewise, see, let this is your point charge having charge Q. This is your point charge, and this charge have, as we have read earlier, the lines of forces due to point charge are your radially outward like this. So this is the direction of electric field lines. So locus of all the points which are at same potential. So if we are taking a points which are at equidistant from the point charge, so we will have spherical equipotential surfaces. So these are spherical EPS, equipotential surface. So point charge or spherical charge body that produces spherical equipotential surface. Similarly, if we are going very far away from that point charge, so our radius of curvature of the spherical surface will increases. So at infinity, radius of curvature will be infinity. So that become your just like your plane equipotential surface. So we can write when source of electric field is at infinity, then we will get plane equipotential surface. plane EPS. Plane EPS means the curvature of that will be infinity, like this. These are plane EPS. Likewise, these all can be said as a plane equipotential surfaces. Similarly, if we are considering our line source, then see the shape of EPS. Line source of electric field. Let this be your any charge body or linear charge conductor, and this is producing electric field like this. So, line source of electric field produces cylindrical EPS. If we are joining those points which are at same potential, so we will get this type of cylindrical surfaces. So, these are your cylindrical EPS. So, in this manner we can say, or we can get our equipotential surface. So, as per the definition of equipotential surface, the locus of the points which are at same potential, those surfaces or those locus give us the EPS. And what we found, if a charge is point charge, then spherical equipotential surface. When charge or source of electric field is at infinity, then we are getting plane EPS. And when our source of electric field is cylindrical or line source, then we are getting cylindrical EPS. Now, some another property of EPS. Third point. Third point is this: two equipotential surfaces or two EPS never intersect at any point. Two EPS never intersect. Why? Otherwise at the point of intersection, two normal can be drawn, which represent two direction of electric field at one point, which is not possible. Meaning is that, as we have seen earlier, dV is written as minus E dot dr, or it is your E dr cos theta. So, when theta is equal to 90 degree, so we got V is constant. It means a potential here constant. So, what has been observed from here, perpendicular to electric field, perpendicular to electric field, all points will be at same potential. So when two equipotential surfaces are intersecting each other, so at the point of intersection, two perpendicular to electric field or two normal can be drawn, and which represent two direction of electric field, which is not possible. This is the meaning of this statement. Next point 4. When a charged particle is moving from one point to another point in the same equipotential surface, then the work done on that charged particle will be 0. So we can write, if a charge is moving from one point to another point in the same equipotential surface, then work done on that charged particle will be 0. Then work done on that charged particle will be 0. As we know, change in potential energy and potential has been defined. The change in potential energy per unit charge is equal to your dV, and change in potential energy is defined as negative of the work done. So minus dW by Q naught is your dV. So we can say work done is equal to your minus of Q naught dV. Now, if a charged particle is moving in a same equipotential surface, so dV will be 0. So for EPS, dV will be 0. So that gives us work done will be 0. It means if charged particle is moving from one point to another point in the same EPS, the work done on that charged particle will be 0. So these are the few major characteristics of equipotential surfaces, and that surface has been made to satisfy our electric field characteristic.